Welcome to my channel Cherish Physics. Subscribe my channel and keep watching. The linear momentum and position vector of the planet is perpendicular to each other at. According to Kepler's law of planetary motion, each planet revolves around the sun in an elliptical orbit. Consider this is a planet. This planet revolving around the sun in the elliptical orbit. When the planet is at this point, that is very near to the sun, which is called as perihelion, and when the planet which is at the position A, the point A is further away from the sun, so the point A is called as aphelion. The P is the perihelion point and A is the aphelion point. First, let us consider the perihelion point. The distance between the sun and the planet, which is called the position vector, and if you draw a tangent at this point P, it gives the velocity. The angle between the position vector and the velocity is 90 degree. Now let us consider another point here, and this is the position vector and this is the velocity line, and if we consider the angle here means it is not 90 degree. And now let us consider the point the planet is here. Likewise, the angle is not 90 degree between the radius vector and the velocity. And now come to the point aphelion point. This is the aphelion point and this is the velocity line, that is tangent drawn on the surface gives the velocity. The angle between the position vector and the velocity is 90 degree. The linear momentum vector depends upon the velocity. So the linear momentum and position vector of the planet is perpendicular to each other at perihelion and aphelion. Second question. If the masses of the earth and sun suddenly double, the gravitational force between them will. We know the equation Newton's law of gravitational force, F equal to G into mass of the earth into mass of the sun by r squared. In the given question, the mass of the earth is doubled and the mass of the sun is also doubled. So F dash equal to G into 2me into 2ms by r squared. So we get 4 into G me ms by r squared. So F dash equal to 4F. So the force increases by 4 times the original force. A planet moving along an elliptical orbit is closest to the sun at distance r1 and farther away at a distance of r2. If v1 and v2 are linear speeds at these points respectively, then the ratio v1 by v2 is. According to the law of conservation of angular momentum, mv1 r1 equal to mv2 r2. So v1 by v2 equal to r2 by r1. Then the ratio v1 by v2 is r2 by r1. Fourth question. The time period of a satellite orbiting the earth in a circular orbit is independent of. We know the formula t equal to 2 pi root of re by g. So the time period t depends upon the radius of the earth and the acceleration due to gravity. So the time period is independent of the mass of the satellite because it depends upon the radius of the orbit. Fifth question. If the distance between the earth and sun were to be doubled from its present value, the number of days in a year would be. According to the Kepler's law of period, t squared is directly proportional to a cube. So a is the semi-major axis of the ellipse. So t squared by a cube equal to constant. This implies t1 squared by a1 cube equal to t2 squared by a2 cube. So t1 is the original time period when the distance between the sun and the earth were to be doubled. Its time period is t2. So t2 squared is equal to a2 by a1 the whole cube into t1 squared. In the given question, the distance gets doubled, so a2 equal to 2a1. So t2 squared is equal to 2 in the place of a2 we have to substitute 2a1. So 2a1 by a1 the whole cube into t1 squared. 52 squared is equal to 2 cube, it is 8, t1 squared. T1 is the original time period. So 1 year is equal to 365 days. So 8 into 365 the whole squared. So t2 equal to, we have to take the square root. 365 into root of 8. Root of 8 its value is 2 into root 2. Root 2 is 1.414. So t2 equal to 365 into 2 into 1.414, which is equal to 1032.22. So the number of days in the year is 1032.